formula. Okay, you can refer to my slide in page 5 for the example question. Okay, from this question, okay, this is the question. So given that the heat formula or the heat equation for this question is du dt equal to the square u over dx square. Okay, the limit is for x between 0 to 2 meter, and the time for the approximation must be more than 0 second. Okay, and also given that the boundary condition, okay, for at the first boundary, when the value of x is 0, okay, the t value is equal to te negative t, t exponent negative t. Okay, and for the second boundary, when the x is equal to 2, okay, the condition at the boundary is equal to t. Okay, this is applicable for the t value more than 0 second. And also given by the question, for the initial condition, okay, so the initial value of heat on the rod, okay, is given by this condition. Okay, for u, temperature for at the position of x at the value of t is 0 is x, okay, is equal to x. This is for the rod between point x equal to 0 to x equal to 1. And the second condition given by 2 minus x, this is for the point on the rod between the position at x equal to 1 to 2. Okay, so all this information given, you have to sketch the rod diagram and state all the value for the boundary condition and initial condition before you do the approximation. And also given by the question, the time for the approximation that you need to do is for t less or equal to 0.25 second, and at the x-axis, okay, the interval or the step size or the distance between one point to the other point is equal to 0.5, and also the value at y-axis, which represent the time, is 0.25 second. Okay, so for the first step, for you to do the solution, you have to draw or sketch the diagram for the heat for the rod, and put all the necessary information given by the question into the diagram, okay, before you can do the approximation using the implicit or Crank-Nicholson method. Okay, right now I'm going to show you on how you can sketch the diagram for the heat movement on the rod, or how you're going to plot your diagram, okay, before you do the approximation. So this is basically your axis. This is your x-axis, which represent the length of the rod in meter or centimeter, and this is your y-axis, which represent the time in second. Okay, so your rod, this is your rod, okay, at initial position, okay, or before you do the approximation. So this is your rod. Okay, your rod, the length of your rod is actually 2 meter. Okay, so this is 0 meter and this is 2 meter. Yeah. And also in between, for the interval at the x-axis is given by the question as 0.5. Okay, so meaning that you will have several points on the rod which represent the length of each point or the distance between each point. So this is your first point at 0.5 meter, and this is at 1 meter. Here is 1.5 meter, and over here is 2 meter. Okay, so you know that the interval or the delta x is equal to 0.5 meter. Delta x also represent the the hash value, okay, for heat equation. Okay, at the y-axis, so for the y-axis, it's given that the delta t or the k. Okay, delta t or your k value is 0.25 second. So if at the first line over here is considered as your initial condition, which at 0 second, so you will have another line, okay, which represent 0.25 second because your interval is 0.25 second, okay, given by the question. Okay, so at this line, okay, this is where you have to do the approximation for the heat value, okay, along the road at the same position, okay, which you have marked earlier, okay, for the according to the delta I or according to the interval or the location of the point given by the question. So the same road, okay, what is the value of temperature at each point, okay, on the road, okay, after 0.25 second. This is what the question wants you to find out. And in the question, it's given that at for the boundary condition. So basically for this road, you have two boundaries. Okay, the two boundaries is actually the two ends of the road. At the first point or the first at this point, and also at the second end of the road at this point. Okay. For boundary at the first point or at 0 x equal to 0, okay, it's given that the condition over here at the boundary is 0 t, okay, where the value is equal to t exponent negative t, okay, and also given the condition over here or the condition given by the question is this is only applicable for t more than 0. Okay, for t more than 0, meaning that it's only involved t equal to 0.25 second. So the value over here is not included. So what you will get from the first boundary condition is actually the value at this point. Okay, over here. The heat value over here at this point. Okay, and the second condition given for the boundary condition is to the temperature, okay, temperature at x equal to 2, okay, for t, and this is equal to t. Okay, the same as the first boundary, this is only applicable for t more than 0. So meaning that what you will get over here is actually the value at the second boundary for t at 0.25 second at this point. Okay, these two value you will get from the boundary condition. Now you can calculate the boundary condition over here. Okay, for t in negative t, okay, use your calculator to do the approximation. The t is 0.25, okay, exponent negative t. So value over here you will get 0.195. Okay, so this is in degrees Celsius. And also for the boundary condition over here, the value of the heat will be 0.25 degrees Celsius because the value is equal to t. So because t is 0.25, so the value over here is 0.25 degrees Celsius. Alright, now you have done for the boundary condition. Let's go to the next one, which is the initial condition. Okay, so for initial condition, so this is actually represent the value of the road before you do the measurement. Okay, the value of temperature on the road at the mark points, okay, over here at the 5 point over here, before you do the approximation for t more than 0. Okay, at t equal to 0, what are the value over here? Okay, this is what you get from the initial condition. So from the question is given that for at the initial condition, okay, you have two conditions being given. First, it's for okay, I write over here. Sorry, over here. Okay, first is for the case where your x is between 0 to 1. So x between 0 to 1, the initial condition over here is given by x. Okay, so meaning that the value of heat over here at the point 0, 0.5 and 1 meter is equal to the x value. So here will be 0 degrees Celsius, over here is 0.5 degrees Celsius, and here is 1.0 degrees Celsius. And the second condition given by the question is represent the value of heat for x between 1 to 2. Okay, so this is x1, this is x2. So the second initial condition is given by 2 minus x. So for you to find the value over here, you have to use this formula or 2 minus x formula. Okay, so for here 2 minus x is equal to 1. Over here 2 minus 1.5 is equal to 0.5. And at the last point over here, 2 minus 2 is equal to 0 degree Celsius. Okay, right. Now your diagram is almost complete. You already have the value of heat for the boundary condition for t more than 0. And also you already have the value for the initial condition or the temperature on the road at initial time, which is when t equal to 0. Okay, as what you have calculated. Okay, then you can move to the next step where you can approximate the value for heat value over here for the unknown's position. Okay, or at the point which you mark unknown over here. Okay, now we will use the Crank-Nicholson molecule formula to do the approximation for these 3 points. So this is your Crank-Nicholson simplified formula. You can find this formula in my slide. Okay, so this is the simplified formula. So what you need to do from this formula is you have to replace all the unknowns value given in the formula, which is k, hash and c. Okay, the value for k, hash and hash you can find from the equation. And the value for c, actually you have to go back to the given heat equation formula in the question. Okay, over here this is the heat equation formula given by the question. So if you compare this equation, the given equation in the question, with the general heat equation formula. Okay, so this is the general heat equation formula. Okay, you just ignore the value inside the bracket. Okay, so this is the general heat equation formula. So basically C is the coefficient which in front of the derivation formula. Okay, so meaning that the value in front of d squared u over dx squared is the value that represents the C. And for this question, okay, since the value is 1, so meaning that we don't have any numbers over here, so we assume the value of C is equal to 1, meaning that the value of C square over here will be 1 square root, 1 powered by 2 or 1, okay, which equal to 1. So you just replace all the C, K and also hash value into the simplified Crank-Nicholson formula and simplify the whole formula, okay, so that it will be formed in the format of top equal to bottom, okay, which is a must for you to produce when you are using the Crank-Nicholson formula. So I'm going to show you. Okay, so now you just simplify everything inside here. Okay, and okay, so minus uij divide by k is 0.25 equal to c is 1 square over 2. Okay, ui minus 1 j plus 1 minus 2 ui j plus 1 plus ui plus 1 j plus 1. Okay, divide by hash square is 0.5 square. Okay, so plus ui minus 1 j minus 2 ui j plus ui plus 1 j divide by hash square is 0.5 square. Okay, so from here, simplify the equation until you can get in the form of top equal to bottom. What is top equal to bottom? So you have to look at the coordinate for u. So refer to refer to this one. Okay, you must organize the last formula, the last equation that you have created from the simplified Crank-Nicholson formula. Okay, after you replace the value for r, k, and also c. Okay, you must make the formula in a form of top equal to bottom according to the position or the coordinate of the molecule. Okay, over here like this. So you have to rearrange and simplify your final formula over here, final equation over here in the form of top equal to bottom. Okay, so I will show it after this. Alright, now refer to my slide on page 8 for the chapter 9 part 2. Okay, so this is actually what I have done from the previous explanation. Okay, so here this is the formula or the simplified Crank-Nicholson formula, which I already filled the value for k and also hash and also c. So this is the formula. From here, I will simplify the equation so that it will become in the form of top. This is top, okay, equal to bottom. So how am I going to know which one is top and which one is bottom is actually, Okay, it's actually look at the coordinate, okay, I and j. Okay, if for the top coordinate, meaning that the value of j must be in the form of j plus 1 coordinate. Okay, and bottom position is at j. Okay, j coordinate. So I have to rearrange, simplify the equation, okay, and rearrange back the value, okay, according to the coordinate. So everything on my left, on my right is at the position of j plus 1. So this is j plus 1, this is j plus 1, and this is also j plus 1. And the value at my left, my left hand side or right hand side over here is j, the value at the coordinate j. Okay, so when I have arranged like this, then I can transform it into the molecule formula like this. Okay, this is the molecule formula which I create based on this final simplified molecule equation. Okay, from here, as I mentioned, it must be in the form of top equal to bottom. For the top one, this is u. Okay, u I minus 1, j plus 1. I minus 1 is position over here. Okay, j plus 1 is here. Okay, this is at position j plus 1. This is at position j. This is I. Okay, this is I minus 1. This is I plus 1 position. Right? So, meaning that you just put the value inside for here. Okay, this is u, meaning that this is minus 1. Okay, minus 1. For position I, j plus 1, this is I, j plus 1 position. The value is 4. Okay, I put 4 inside the box. And also for the I plus 1, j plus 1, the value is negative 1. So this is negative 1. Equal, so this is equal to u, I minus 1, j. I minus 1 is over here. Okay, so the value is 1, positive 1. I don't have any any value at position u, I, j. So because over here, I only have I minus 1j and I plus 1j. So meaning that for this one is 0 and plus 1 for at position of I plus 1j. So this is plus 1. So from the final molecule equation that you have created from the simplified Crank-Nicholson formula, you can transfer it into the molecule formula so that you can use this molecule formula to do the approximation on the next step. So this is your diagram, okay, which I already showed you before how to sketch the diagram. So this is your diagram. All information for the initial condition. So the initial condition is shown here, and also the boundary condition for here and this one, and this position, okay, is given or has been calculated earlier, okay, before you do the molecule formula, okay, before you produce the molecule formula, okay, meaning that from this diagram, we know that you only have 3 positions or 3 points that you don't have the value, okay, on the white box over here. Okay, this is the first position that you don't know the value. This one is second position, and this is the third position. Okay, so how you going to do the approximation is by using your molecule formula which you have created from the simplified Crank-Nicholson formula which you have used to do the calculation. Okay, so from here, what you